A single German torpedo could shatter a steel hull in moments. Within minutes, an entire Allied cargo ship, carrying thousands of tons of critical food, ammunition, and winter gear, would vanish beneath the freezing Atlantic. The loss was immediate and devastating. The math of the war was terrifyingly simple. A U-boat could sink a ship in a matter of minutes, but traditional shipyards required many months to replace it. To survive, the United States had to fundamentally rewrite that equation. American shipyards were quietly engineering a system to transform shipbuilding from a slow, specialized craft into an unstoppable industrial flow. But how do you win a war of attrition when the enemy destroys your supply line faster than you can rebuild it? By the brutal winter of 1940 and 1941, that mathematical terror was threatening to collapse the entire Allied war effort. The survival of the United Kingdom rested exclusively on a single, highly vulnerable lifeline stretching across the dark expanse of the North Atlantic. Food, aviation fuel, raw steel, and heavy munitions had to arrive by sea, or the island nation would be starved into submission. The German naval strategy did not require invading British shores. It only required bleeding this transatlantic artery dry. According to official Maritime Administration records, the German U-boat offensive was achieving exactly that. The attrition rate was catastrophic. British merchant vessels were being hunted, torpedoed, and sent to the bottom at a pace that far exceeded the capacity of their domestic industry. British shipyards, already battered by persistent Luftwaffe bombing raids and constrained by limited steel supplies, simply could not launch replacement hulls fast enough. The math was absolute, and the trajectory was fatal. If Britain was bleeding ships vastly faster than it could build them, the supply line was inevitably going to break. This is the story of how a radically simplified piece of engineering and a massive, unprecedented shift in manufacturing logic broke the back of the German tonnage war. But before this industrial miracle could take shape, the crisis demanded immediate outside intervention. A British trade mission desperately crossed the Atlantic to seek salvation in American shipyards. Yet, when they arrived, they discovered a new, paralyzing conflict. The obvious savior was already overwhelmed, leaving the critical question unanswered: who could possibly hold the line? In late 1940, a British merchant shipbuilding mission, led by seasoned shipbuilder Robert Cyril Thompson, arrived on American soil. They did not come seeking vague, abstract assistance. They stepped off the boat carrying a very specific, meticulously detailed set of blueprints rolled tightly under their arms. This was the design for what would become known as the Ocean-class freighter. The British had designed a heavy workhorse, a 10,000-ton cargo ship, engineered for rugged reliability under extreme wartime duress. Crucially, the British design relied on coal-fired boilers rather than oil. The reasoning was simple and desperate. Britain had vast domestic coal reserves, but had to import every single drop of fuel oil through the U-boat-infested waters of the Atlantic. The mission's mandate from London was straightforward on paper: secure contracts with American firms to build 60 of these vessels, pay for them in hard cash, and get them integrated into the Atlantic supply chain as fast as humanly possible. To the officials sitting in London, the United States was a vast, untouched industrial sanctuary, safely beyond the reach of the Luftwaffe, seemingly capable of easily absorbing a modest order of 60 cargo ships. The American maritime establishment, however, viewed the British blueprints with a mix of professional curiosity and mild disdain. The United States Maritime Commission, operating under the ambitious Merchant Marine Act of 1936, was already deep into a long-range, federally funded program to modernize the American commercial fleet. They were building the C-type cargo vessels, ships that were fast, sleek, oil-burning, and packed with the latest maritime technology. To American naval engineers, the British Ocean-class design looked like a relic from a bygone era, a slow, utilitarian steel box designed for a time before modern propulsion. But regardless of design preferences or national pride, the British mission hit an immediate, insurmountable brick wall. The persistent illusion that America was a sleeping industrial giant with unlimited, idle capacity evaporated the moment Thompson and his team began touring the major coastal shipyards. The United States was not officially at war, but its heavy industry was already redlining. In July 1940, the U.S. Congress had authorized the Two-Ocean Navy Act, a colossal, unprecedented expansion of naval power designed to simultaneously dominate both the Atlantic and the Pacific theaters. Every established legacy shipyard in the country, Massive complexes like the Brooklyn Navy Yard, Newport News Shipbuilding and Dry Dock in Virginia, Mare Island in California, and Bath Iron Works in Maine was completely choked with fresh keels. They were actively constructing massive Essex-class aircraft carriers, Iowa-class battleships, heavy cruisers, and scores of fleet destroyers. Furthermore, the Maritime Commission's own civilian C-type freighters were occupying whatever slipways the Navy had not already claimed. Every functional building way, every dry dock, every fitting out basin, and every heavy lift waterfront crane in the United States was booked solid for years into the future. There was absolutely no physical waterfront real estate left to squeeze in a sudden, emergency foreign order for 60 British freighters. The crisis, however, was far deeper than just a lack of empty concrete slipways. It was rooted in the fundamental, centuries-old nature of how ocean-going vessels were constructed. In 1940, shipbuilding was not a modern, industrialized assembly line. It was a highly specialized, generational craft. You did not manufacture a ship. You built it, painstakingly, from the keel up, entirely in place on a massively reinforced, inclined slipway. Once the heavy steel keel was laid down, thousands of individual steel plates had to be individually hoisted into place by cranes, precisely aligned and fastened together by armies of highly skilled riveters. Riveting itself was a demanding, physically brutal, and highly dangerous trade, requiring synchronized four-man teams. A heater had to superheat a steel rivet in a portable coal forge until it glowed cherry red, then use metal tongs to toss it through the air across the scaffolding to a catcher. The catcher snatched the glowing steel in a metal cone, retrieved it with his own tongs, and slotted it into a pre-drilled hole in the overlapping hull plates. On the blind side of the steel plate, working in the claustrophobic dark of the hull, a bucker leaned his entire body weight against a heavy metal bucking bar to hold the rivet firmly in place. Simultaneously, the riveter on the outside drove the glowing steel home with a deafening, bone-rattling pneumatic hammer, crushing the end of the rivet to form a massive, watertight seal. This was an exacting, exhausting choreography of heavy labor. A single missed strike, a rivet that cooled too quickly, or an improperly bucked head meant the steel seal would fail under the immense hydrostatic pressure of the open ocean. You could not teach a farmer or a department store clerk to do this job safely in a week. The American shipbuilding workforce consisted of seasoned tradesmen, shipwrights, loftsmen, and marine architects whose localized skills took years to master. And every single one of those skilled men was already fully employed on American naval and commercial contracts. There was no shadow army of shipbuilders waiting in the wings, even if, by some sheer miracle of logistics, empty waterfront property could be dredged out of swamps, and enough skilled labor could be materialized to rivet 60 steel hulls together. The British mission ran headfirst into an entirely different, completely insurmountable mechanical bottleneck: propulsion. The absolute gold standard for modern, efficient maritime transport was the high-pressure steam turbine. But steam turbines are incredibly complex, delicate pieces of machinery, requiring microscopic machining tolerances and highly specialized metallurgical casting to withstand intense heat and pressure. More importantly, steam turbines inherently spin at thousands of revolutions per minute. A ship's massive bronze propeller, however, is designed to operate efficiently at very low speeds, often well under 100 revolutions per minute. To bridge this violent gap in physics, modern ships required massive, intricately machined reduction gears. Manufacturing these immense reduction gears was one of the most exacting and time-consuming industrial processes on the planet. The massive gear wheels had to be cut with absolute precision in temperature-controlled rooms. A microscopic imperfection of even 1/1000th of an inch would cause the gears to vibrate and shred themselves to pieces under the immense torque of a ship's engines. The specialized American factories capable of cutting these gears, heavy industrial titans like Westinghouse, General Electric, and Alice Chalmers, were already operating 24 hours a day, 7 days a week. Their entire production output was swallowed whole by the demands of the Two-Ocean Navy Act. A single modern battleship or destroyer required massive, multi-stage arrays of these reduction gears, and the United States Navy held absolute, unyielding priority over every factory floor. You could not simply build a new factory to produce reduction gears. The colossal specialized machine tools required to cut the gears took years to construct themselves. The British mission found themselves staring at a logistical dead end. They had blueprints and they had funding, but they had absolutely no way to translate those paper assets into floating steel. The American industrial machine, formidable as it was structurally rigid. It was perfectly tuned to build relatively small numbers of highly sophisticated, custom-crafted vessels using traditional, sequential methods. It was physically incapable of absorbing a sudden order for 60 ships without immediately cannibalizing the existing critical naval buildup. Looming over this entire bureaucratic and industrial nightmare was the terrifying mathematics of the Battle of the Atlantic. The British were fighting for their national survival, asking for just 60 ships. But the brutal reality of the ocean was that 60 ships were barely a temporary stopgap. In the frigid, turbulent waters of the North Atlantic, German U-boat commanders were hunting with devastating, calculated efficiency. By late 1940, the attrition rate was so severe that a fleet of 60 cargo ships could be located, torpedoed, and sent to the bottom of the ocean in a matter of weeks. The British were asking for a bucket of water to extinguish a raging forest fire, and the American shipbuilding industry was forced to admit that they did not even have a bucket to spare. The traditional logic of shipbuilding had completely failed the demands of a mechanized, global war. You could not defeat a relentless campaign of attrition using bespoke, craft-based manufacturing. The traditional shipyards were too slow, too inflexible, and far too dependent on highly trained labor and elite supply chains that were already stretched past their breaking point. To deliver 60 ships, let alone the hundreds or eventually thousands of transport vessels that the grim calculus of the Atlantic would ultimately demand to keep Britain in the fight, someone was going to have to do the impossible. They could not rely on the established, congested legacy shipyards of the East Coast. They would have to figure out a way to power massive ocean-going vessels without using complex steam turbines and impossible to procure reduction gears. And most importantly, they would have to completely abandon the ancient, revered craft of shipbuilding itself. To save the transatlantic supply line, the construction of a 10,000-ton ocean freighter could no longer be treated as a specialized maritime art. It had to be violently disrupted, stripped of its bespoke complexity, and totally reimagined from the ground up as a brutal, relentless exercise in mass manufacturing. On January 3rd, 1941, President Franklin D. Roosevelt shattered the logistical deadlock and fundamentally altered the trajectory of the maritime war. Recognizing that the established maritime industry could not absorb a single additional hull, he bypassed the congested legacy shipyards entirely. Roosevelt announced a staggering emergency program. The United States government would immediately fund the construction of 200 additional cargo vessels. This was not a standard procurement order to be squeezed into existing facilities. This presidential directive mandated the rapid creation of brand new emergency shipyards. These were vast, raw industrial footprints to be carved directly out of coastal mudflats, abandoned rail yards, and empty marshlands from the shores of California to the coast of Maryland. But dredging harbors and pouring concrete slipways was only the first step. To actually fill those new yards with floating steel, the entire American maritime establishment had to swallow its pride and execute a massive, painful pivot in design philosophy. The United States Maritime Commission officially abandoned its pursuit of cutting-edge naval architecture. The engineers stopped trying to build the perfect ship. Instead of sleek, highly crafted, and technologically advanced commercial freighters, they reached backward into engineering history. They took the foundational concept of the British ocean-class blueprints, the simple, utilitarian workhorse the British trade mission had desperately brought across the Atlantic, and heavily modified it specifically for American mass manufacturing. This new, localized blueprint was officially designated the EC2-S-C1, a vessel the world would soon recognize as the Liberty ship. The modifications were strategic and ruthless. While the British Ocean class was designed to burn coal to accommodate the United Kingdom's domestic fuel supplies, the American EC-2 was adapted to run on oil, eliminating the need for massive coal bunkers and a small army of stokers. But beyond the fuel source, the Liberty ship represented a total, unapologetic rejection of traditional maritime aesthetics and modern performance. It was deliberately stripped of complex compound curves, elegant shear lines, and advanced propulsion systems. In the eyes of traditional naval architects, it was a profound step backward. It was unrefined. Its internal layout was Spartan, and it lumbered through the water. Top maritime engineers openly mocked its blunt, boxy profile, and even the president infamously referred to it as a dreadful-looking object. But elegance and speed had no place in a mathematical war of attrition. The core conflict at the heart of the EC-2 design was the deliberate, highly calculated abandonment of quality in favor of overwhelming quantity. The peacetime expectation of building highly crafted, fast cargo ships that would last for decades was permanently thrown out the window. The new strategic imperative was not to outrun the German U-boats, nor to build ships capable of surviving torpedo strikes. The strategy was to physically overwhelm the enemy's capacity to sink them. The Maritime Commission intended to flood the Atlantic Ocean with standard, identical, and easily reproducible hulls. They were designing a conveyor belt of expendable steel that the German submarine fleet simply did not have enough torpedoes or time to break. Every single angle, every bulkhead, and every steel plate on the Liberty ship was drafted with one singular obsession: rapid, uncompromising, idiot-proof assembly. The emergency shipyards were being paved. The simplified EC-2 blueprints were drawn, approved, and rapidly distributed across the country. The United States government had boldly committed to breaking the German naval blockade with an endless armada of standardized hulls. Yet, a massive, gaping hole remained in the logic of the emergency shipbuilding program. Having a simplified blueprint unrolled on a drafting table is one thing, but how do you actually construct hundreds of massive ocean-going transports at record speed when the traditional slipways are full, the experienced shipwrights are already drafted into naval construction, and the heavy factories producing complex engine parts are completely tapped out? The design demanded mass production, but the physical mechanism to achieve that production did not yet exist. To solve the mechanical bottleneck, American industrialists had to entirely destroy the centuries-old concept of what a shipyard was fundamentally supposed to be. Historically, a ship was a piece of architecture, treated much like a cathedral. You laid a heavy steel keel on an inclined wooden slipway, built a massive, complex network of wooden scaffolding around it, and then slowly brought thousands of tiny, individual pieces of steel to that single, static location. This created an unavoidable, paralyzing spatial traffic jam. You could only fit a limited number of men around the hull, and they could only work in a strict, sequential order. The revolutionary answer to this bottleneck was to stop treating the vessel as a building and start treating it as a product of an assembly line. The newly commissioned emergency shipyards were not traditional maritime facilities squeezed onto rocky coastlines. They were sprawling, horizontal outdoor factories scraped out of vast expanses of tidal mudflats, abandoned rail yards, and empty coastal marshlands. Instead of bringing individual steel plates to the congested slipway, workers brought the raw steel to massive, open-air prefabrication sheds positioned hundreds of yards inland. Here, on flat ground, sheltered from the unpredictable coastal weather and free from the cramped, dangerous heights of slipway scaffolding, the magic of mass manufacturing took hold. Workers began welding smaller steel plates together to form massive, multi-ton subassemblies. Entire transverse bulkheads, towering sections of the deckhouse, and intricately curved bow assemblies. This inland prefabrication offered a massive, hidden physical advantage. By building these giant blocks on the ground, workers could manipulate them, flipping them upside down or laying them on their sides using heavy mechanical rollers. This allowed the welders to almost exclusively perform what was known as downhand welding. Instead of fighting gravity, straining their necks to weld overhead while molten slag dripped down onto their leather aprons, they could weld looking down, letting gravity naturally pull the liquid metal deep into the seam. This not only created a vastly stronger structural bond, but it also multiplied the speed of the work exponentially. reducing a process that once took days into a matter of hours. Once a massive 50-ton steel subassembly was entirely finished, inspected, and painted in the prefabrication yard, it was hoisted onto heavy flatbed rail cars. These rail cars then rolled the massive blocks directly out to the actual slipway. Looming over these slipways were gigantic, specialized heavy lift machines known as whirly cranes, capable of rotating a full 360 degrees while carrying immense loads. These towering cranes would hook onto the 50-ton deckhouse or bow section, hoist it high into the air, and swing it delicately out over the water. The massive block would then drop precisely into its designated slot on the waiting hull, where it would be swiftly welded into place. The slipway was no longer a construction site. It was merely the final point of connection. This breathtaking choreography of heavy lifting allowed thousands of people to work on the exact same ship simultaneously, spread out across hundreds of acres of industrial park, completely bypassing the spatial limitations that had governed shipbuilding since the age of sail. Yet, assembling a massive steel shell at record speed was entirely useless if you could not make it move across the ocean. The American maritime industry was still completely paralyzed by the lack of modern steam turbines and the microscopic precision required for reduction gears. The solution for the Liberty ship was a highly calculated, deliberate technological regression. Recognizing that modern propulsion was a catastrophic bottleneck, the Maritime Commission reached back over half a century into engineering history. They bypassed the sleek, high-speed turbines and selected the massive, antiquated triple-expansion steam engine. To a modern naval architect, this engine was a towering, 3-story high mechanical dinosaur, a relic from the late 19th century. It operated by feeding pressurized steam sequentially through 3 progressively larger cast-iron cylinders, high pressure, intermediate pressure, and low pressure, extracting every possible ounce of kinetic energy from the expanding steam before finally condensing it back into water. It was loud, incredibly heavy, and visibly vibrated with massive, exposed, moving parts that required constant manual lubrication. But strategically, within the context of a global industrial war, the triple expansion engine was an absolute masterpiece of logistics. Because the core technology was 50 years old, the patents were public, the blueprints were universally understood, and most importantly, the manufacturing tolerances were incredibly forgiving. You did not need a specialized, climate-controlled, state-of-the-art East Coast factory equipped with rare machine tools to build a triple expansion engine. You could farm the massive contracts out to the deep American interior. Suddenly, locomotive factories in Ohio, heavy iron foundries in Pennsylvania, and agricultural tractor plants across the Midwest were aggressively repurposed. These inland factories, which had never seen the ocean and previously manufactured train wheels or farming plows, began casting massive engine blocks and forging giant, heavy steel crankshafts. They loaded the finished 3-story engines onto heavy freight trains and sent them rolling across the country toward the coasts. By accepting an older technology, the Maritime Commission had instantly unlocked the entire heavy industrial base of the American heartland, completely bypassing the coastal turbine bottleneck. This brilliant logistical maneuver, however, demanded a brutal, terrifying trade-off on the open water. A Liberty ship, pushed by its thumping triple expansion engine, lumbered through the ocean at a maximum top speed of just 11 knots. That equates to roughly 12.5 miles per hour. In the lethal environment of the North Atlantic, 11 knots was agonizingly slow. A surface German U-boat could comfortably travel at 17 knots on its diesel engines, easily outrunning, outmaneuvering, and intercepting the American freighters. The Liberty ship was essentially a sitting duck, incapable of outrunning its predators. But the speed was the sacrificial lamb offered in exchange for guaranteed, massive hauling capacity. That slow, rhythmic engine could reliably push a heavily laden hull packed with roughly 10,800 deadweight tons of cargo. That payload was the entire point of the vessel's existence. 10,800 deadweight tons equated to a staggering logistical footprint. It meant carrying nearly 300 Sherman tanks in a single crossing. It meant transporting enough field rations to feed an entire infantry division for months, alongside thousands of crates of artillery shells, heavy trucks, medical supplies, and millions of gallons of aviation fuel stored in deck drums. The Liberty ship was not designed to run away from the enemy. It was designed to carry an overwhelming, crushing weight of material into the war zone. To physically fuse these heavy engines and thousands of steel plates together, the emergency shipyards faced their most severe deficit of all: human capital. The skilled shipwrights, the master pipe fitters, and the veteran riveting crews were already gone, swallowed whole by the United States Navy's massive warship expansion. The Liberty Ship program required a shadow army of labor, a workforce of hundreds of thousands of people that simply did not exist in 1941. The solution was the radical de-skilling of maritime labor. The intricate, localized knowledge of the traditional shipbuilder was meticulously broken down into hyper-specific, highly repetitive, easily teachable micro-tasks. Furthermore, the brutal, highly specialized art of riveting, which required a synchronized four-man team and years of physical coordination to master, was almost entirely replaced by welding. Welding was the technological savior of the emergency labor program. Instead of four men heating, tossing, catching, and pneumatic hammering a single rivet, a single worker equipped with an electric welding torch could fuse two plates of steel together significantly faster, creating a lighter, more rigid, and completely watertight hull. More importantly, you could teach the foundational basics of arc welding to a complete novice in a matter of weeks. This low barrier to entry triggered one of the greatest and most rapid demographic shifts in American industrial history. The emergency shipyards became a massive magnet for populations previously excluded from heavy industry. Desperate for hands to fill the sprawling yards, the shipyards hired women by the tens of thousands, placing them inside claustrophobic double-bottom hulls with heavy leather gloves, a welding mask, and an electric stinger. African Americans, escaping the segregated poverty, violence, and sharecropping systems of the Jim Crow South in the second wave of the Great Migration, moved by the thousands to the coastal yards to take on grueling, dangerous shifts in the steel staging areas. Short-order cooks, school teachers, and displaced farmhands from the Dust Bowl flooded into the booming coastal cities of California, Oregon, and Maryland. These new workers did not know how to build a ship, and the genius of the system was that they did not need to. A female welder working the graveyard shift was not asked to understand complex naval architecture, buoyancy, or the hydrodynamics of the hull. She was asked to weld one specific 30-foot seam on one specific deckhouse bulkhead, and to execute that single task perfectly, day after day, hundreds of times in a row. The physical reality of this work was a grinding sensory overload. The shipyards operated 24 hours a day, 7 days a week, running on 3 massive shifts to keep the steel moving. Through the dead of night, the coastal skies glowed with the eerie, flickering blue light of 10,000 electrical arcs. The air was thick with the acrid smell of burning flux, melting steel, and the deafening, rhythmic slamming of heavy metal plates being dropped into position by the whirly cranes. Inside the unventilated steel compartments of the lower hull, temperatures soared, and the air filled with toxic fumes as welders crawled on their hands and knees over jagged steel edges. Workers suffered from welder's flash, their eyes burning from accidental exposure to the intense ultraviolet light of the arcs. Yet, by isolating the labor into highly repetitive loops, the emergency shipbuilding system successfully transformed untrained civilians into hyper-specialized cogs within a massive, relentless industrial machine. They digitized the labor, turning a craft of 1,000 variables into a factory line of binary, repeatable actions. When this trinity of innovations, the vast prefabrication choreography, the decentralized inland engine manufacturing, and the de-skilled, hyper-specialized mass labor force finally synchronized, the physical results defied the fundamental, accepted laws of traditional manufacturing. In the early, chaotic days of the emergency program in 1941, the learning curve was steep and painful. It initially took an average of well over 230 days to lay a keel, assemble the hull, install the antiquated steam engine, and launch a single Liberty vessel. That was over 7 months of grinding labor just to put one slow target into the water. But as the decentralized Midwestern foundries hit their stride, delivering engines perfectly on schedule, as the prefabrication yards perfected the logistical sequence of their massive heavy-lift cranes, and as the diverse, newly trained workforce gained pure muscle memory, the timeline began to violently collapse. The learning curve went practically vertical. The shipyards stopped behaving like chaotic construction sites and began operating like highly tuned, relentless extrusion machines. The time it took to build a ship dropped from 230 days down to 150 days, and then plummeted past 100. By the critical years of 1943 and heading into 1944, the sprawling emergency shipyards on all three American coasts had hammered the average construction time of a 10,000-ton ocean freighter down to roughly 40 days. Think about the physical reality of that pace. An empty, rain-slicked concrete slipway would receive a massive steel keel. Just over a single month later, a fully functioning, multi-decked, steam-powered cargo behemoth, painted in slate-gray camouflage and ready to load ammunition, would slide backward into the cold ocean water. And the very next morning, before the water had even settled in the basin, the massive cranes would drop a brand new keel onto that exact same slipway, and the 40-day clock would violently start all over again. It was a staggering, unprecedented compression of time, labor, and steel, creating an industrial momentum that the world had never witnessed. 3,000 miles away, in the freezing, violent, and blood-stained waters of the North Atlantic, the German U-boat commanders were entirely blind to this manufacturing revolution. Deep beneath the surface of the ocean, encapsulated in steel tubes reeking of diesel fumes, unwashed bodies, and battery acid, the German captains were operating strictly on the traditional, established mathematics of naval warfare. Staring through the optics of an attack periscope, watching a torpedo detonate against the side of an Allied freighter, they were meticulously tallying their kills in their official war diaries. They were calculating the exact tonnage they had sent to the bottom, reporting the numbers back to headquarters, and projecting the inevitable mathematical starvation of the British Isles. The German Strategic Command, operating under the ruthless logic of Admiral Karl Donitz, relied on a simple, historically proven premise. A well-placed submarine could locate, track, and sink a 10,000-ton cargo ship in a single afternoon. That same ship, according to all known laws of global heavy industry, should take at least half a year, if not longer, to replace. Therefore, Germany did not need to win grand surface battles. Victory through pure, relentless attrition was a mathematical certainty. Every time a torpedo struck home, tearing a fatal hole beneath the waterline and sending a cargo ship plunging into the abyssal depths, the U-boat crews believed they were permanently subtracting from the Allied ledger. They believed they were slowly, methodically suffocating the enemy's fundamental ability to wage war. What the German High Command could not comprehend, because it had never existed before in the history of human conflict, was that the ledger was no longer governed by the rules of craft. They were not fighting a finite fleet of bespoke merchant vessels. They were unknowingly fighting a sprawling, continental-scale industrial machine that had learned to replace a shattered freighter faster than a German submarine could expend its torpedoes, transit back to a fortified concrete pen in occupied France, and reload its tubes. The U-boats were aggressively and bravely cutting the heads off a hydra, completely unaware that the monster was regenerating at an impossible, exponential rate just beyond the horizon. But a sobering, terrifying reality remained for the Allied High Command, casting a dark shadow over the glaring arc lights of the American shipyards. A Liberty ship sliding down a concrete slipway in California or Maryland in just 40 days was an absolute, undeniable triumph of engineering, logistics, and human labor. But once that ship left the safety of the coastal waters, it was just an unarmored, slow-moving steel box lumbering across a hostile ocean at 11 knots. It was still highly flammable. It was still easily tracked by sonar and hydrophones, and it was still structurally catastrophic when subjected to the explosive shockwave of a German torpedo. The industrial production was soaring, and the identical replacement hulls were flooding into the water by the hundreds. But did raw industrial output alone guarantee survival against a well-aimed torpedo in the dark? We must reveal the peak production in 1943, up to 3 Liberty ships a day, discuss the SS Robert E. Peary as a staged stunt, and emphasize the grim reality. Launching ships did not make them invincible. U-boats still sank them, and thousands of mariners died. Output alone didn't defeat the submarines. In 1943, the sheer scale of the emergency shipbuilding program reached its absolute dizzying zenith. Across the United States, from the massive Richmond shipyards in California to the sprawling complexes in Baltimore, the combined industrial effort achieved a rate of production that completely shattered the fundamental laws of maritime physics. At the absolute peak of the program, the emergency yards were successfully launching up to 3 fully assembled Liberty ships every single day. That was three massive 10,000-ton cargo freighters sliding into the water every 24 hours. This industrial momentum generated some of the most famous wartime propaganda of the era, deliberately engineered to crush German morale and project American invincibility. The most legendary spectacle occurred with the SS Robert E. Peary. In a highly choreographed, breathless display of manufacturing dominance, the shipyard workers laid the keel, welded the hull, installed the engine, and launched the vessel in an astonishing 4 days and 15.5 hours. It was a stunning headline, broadcast around the world. But beneath the glaring flashbulbs and the patriotic newsreels, the 4-day launch was a carefully staged, meticulously pre-assembled stunt. The ship still required nearly a week of final fitting out before it could actually be handed over for service. More importantly, it masked a grim, underlying reality that the propaganda machines desperately wanted to ignore. Building a Liberty ship in 40 days, or even launching one in 4, did not miraculously grant it armor plating or increase its agonizingly slow 11-knot top speed. Pumping out identical steel hulls absolutely solved the mathematical crisis of replacing lost tonnage, but a manufactured ship was completely, utterly useless if its critical cargo ended up resting at the bottom of the ocean before it ever reached the shores of Europe. Launching ships did not make them invincible. The German U-boats did not simply disappear because the Americans were building faster. The underwater predators continued their deadly, relentless attacks throughout the Atlantic. Torpedoes continued to tear through the thin steel plating of the Liberty ships, igniting aviation fuel and detonating ammunition holds in the dark, freezing waters. Thousands of American merchant mariners would ultimately die agonizing deaths, attempting to navigate these slow, vulnerable targets across a hostile ocean. The harsh truth of the tonnage war was that shipyards do not sink submarines. You cannot weld your way out of a torpedo strike, and you cannot drown a U-boat under a pile of fresh blueprints. The industrial miracle of the emergency shipyards ensured that the Allies had enough vessels to keep trying, but it did not guarantee that those vessels would actually survive the crossing. The core conflict remained dangerously unresolved. If the shipyards were relentlessly wasполнять, replenishing the fleet, but German torpedoes were still finding their targets and shattering hulls, what actually stopped the slaughter? If the ships were still sinking, what truly turned the tide in the Atlantic? Word count check. In 1943, the sheer scale of the emergency shipbuilding program reached its absolute, dizzying zenith. Across the United States, from the massive Richmond shipyards in California to the sprawling complexes in Baltimore, the combined industrial effort achieved a rate of production that completely shattered the fundamental laws of maritime physics. At the absolute peak of the program, the emergency yards were successfully launching up to 3 fully assembled Liberty ships every single day. That was 3 massive 10,000-ton cargo freighters sliding into the water every 24 hours. This industrial momentum generated some of the most famous wartime propaganda of the era, deliberately engineered to crush German morale and project American invincibility. The most legendary spectacle occurred with the SS Robert E. Peary. In a highly choreographed, breathless display of manufacturing dominance, the shipyard workers laid the keel, welded the hull, installed the engine, and launched the vessel in an astonishing 4 days and 15.5 hours. It was a stunning headline, broadcast around the world. But beneath the glaring flashbulbs and the patriotic newsreels, the 4-day launch was a carefully staged, meticulously pre-assembled stunt. The ship still required roughly a week of final fitting out before it could actually be handed over for service. More importantly, it masked a grim, underlying reality that the propaganda machines desperately wanted to ignore. Building a Liberty ship in 40 days, or even launching a pre-staged hull in 4, did not miraculously grant it armor plating or increase its agonizingly slow 11-knot top speed. Pumping out identical steel hulls absolutely solved the mathematical crisis of replacing lost tonnage, but a manufactured ship was completely, utterly useless if its critical cargo ended up resting at the bottom of the ocean before it ever reached the shores of Europe. Launching ships did not make them invincible. The German U-boats did not simply disappear because the Americans were building faster. The underwater predators continued their deadly, relentless attacks throughout the Atlantic. Torpedoes continued to tear through the thin steel plating of the Liberty ships, igniting aviation fuel and detonating ammunition holds in the dark, freezing waters. Thousands of American merchant mariners would ultimately die attempting to navigate these slow, vulnerable targets across a hostile ocean. The harsh truth of the tonnage war was that shipyards do not sink submarines. You cannot weld your way out of a torpedo strike, and you cannot drown a U-boat under a pile of fresh blueprints. The industrial miracle of the emergency shipyards ensured that the Allies had enough vessels to keep trying, but it did not guarantee that those vessels would actually survive the crossing. The core conflict remained dangerously unresolved. If the shipyards were relentlessly replenishing the fleet, but German torpedoes were still finding their targets and shattering hulls, what actually stopped the slaughter? If the ships were still sinking, what truly turned the tide in the Atlantic? Total words, 462. Fits the 380 to 510 range perfectly. Time estimate at 130 words per minute, approximately 213 seconds. Fits the 168 to 214 seconds range. Tone is serious, documentary. No Russian text, no headers, no meta notes, no gore. Picks up seamlessly. In 1943, the sheer scale of the emergency shipbuilding program reached its absolute, dizzying zenith. Across the United States, from the massive Richmond shipyards in California to the sprawling complexes in Baltimore, the combined industrial effort achieved a rate of production that completely shattered the fundamental laws of maritime physics. At the absolute peak of the program, the emergency yards were successfully launching up to 3 fully assembled Liberty ships every single day. That was 3 massive 10,000-ton cargo freighters sliding into the water every 24 hours. This industrial momentum generated some of the most famous wartime propaganda of the era, deliberately engineered to crush German morale and project American invincibility. The most legendary spectacle occurred with the SS Robert E. Peary, in a highly choreographed, breathless display of manufacturing dominance. The shipyard workers laid the keel, welded the hull, installed the engine, and launched the vessel in an astonishing 4 days and 15 and a half hours. It was a stunning headline, broadcast around the world. But beneath the glaring flashbulbs and the patriotic newsreels, the 4-day launch was a carefully staged, meticulously pre-assembled stunt. The ship still required roughly a week of final fitting out before it could actually be handed over for service. More importantly, the spectacle masked a grim underlying reality that the propaganda machines desperately wanted to ignore. Building a Liberty ship in 40 days, or even launching a pre-staged hull in 4, did not miraculously grant it armor plating or increase its agonizingly slow 11-knot top speed. Pumping out identical steel hulls absolutely solved the mathematical crisis of replacing lost tonnage, but a manufactured ship was completely, utterly useless if its critical cargo ended up resting at the bottom of the ocean before it ever reached the shores of Europe. Launching ships did not make them invincible. The German U-boats did not simply disappear because the Americans were building faster. The underwater predators continued their deadly, relentless attacks throughout the Atlantic. Torpedoes continued to tear through the thin steel plating of the Liberty ships, igniting aviation fuel and detonating ammunition holds in the dark, freezing waters. Thousands of American merchant mariners would ultimately die attempting to navigate these slow, vulnerable targets across a hostile ocean. The harsh truth of the tonnage war was that shipyards do not sink submarines. You cannot weld your way out of a torpedo strike, and you cannot drown a U-boat under a pile of fresh blueprints. The industrial miracle of the emergency shipyards ensured that the Allies had enough vessels to keep trying, but it did not guarantee that those vessels would actually survive the crossing. The core conflict remained dangerously unresolved. If the shipyards were relentlessly replenishing the fleet, but German torpedoes were still finding their targets and shattering hulls, what actually stopped the slaughter? If the ships were still sinking, what truly turned the tide in the Atlantic? The answer was a lethal convergence of raw industrial output and aggressively evolved naval tactics. The identical steel hulls pouring out of American emergency shipyards were no longer sailing into the Atlantic alone. Instead, these slow-moving Liberty ships were being absorbed into massive, tightly orchestrated convoys, sometimes numbering over 60 vessels, moving in a rigid grid formation. Convoys themselves were not a new concept, but what materialized in the spring of 1943 was a fundamentally different beast. The sheer volume of replacement ships provided the critical mass necessary to construct a highly lethal, multi-layered defensive perimeter around the cargo. The turning point hinged on closing the mid-Atlantic air gap, the vast stretch of ocean where U-boats had previously operated on the surface with total impunity. To bridge this dead zone, the Allies introduced escort carriers, small, mass-produced flight decks that traveled directly alongside the merchant vessels. Suddenly, the lumbering freighters had their own permanent air cover. Simultaneously, long-range patrol aircraft, specifically modified B-24 Liberators, began sweeping the ocean, equipped with a devastating new technology, miniaturized, centimetric radar. For German submarine commanders, the surface of the Atlantic instantly became a trap. When a U-boat surfaced in the dead of night to run its diesel engines and recharge its depleted electric batteries, the invisible sweep of Allied radar would paint its conning tower in the pitch black. Aircraft could now drop out of the night sky, illuminating the submarine with intense searchlights before unleashing payloads of depth charges. With the technological advantage shifting, the entire tactical dynamic of the ocean inverted. The Allies stopped playing purely defensive escort roles and began using the massive convoys as deliberate bait. Because the emergency shipyards back in the United States were churning out replacement vessels at an unstoppable rate, the Allied Naval Command was no longer paralyzed by the fear that losing a single transport would starve the United Kingdom. That unprecedented strategic cushion allowed them to deploy aggressive hunter-killer groups. When a U-boat was detected, destroyers and corvettes no longer had to stay glued to the sides of the Liberty ships. They could detach, hunt down the sonar contact, and relentlessly pursue the submerged submarine until its pressure hull ruptured. This escalating pressure detonated in a decisive climax during the spring of 1943, culminating in a period known as Black May. Admiral Karl Donitz ordered his wolf packs to launch massive, coordinated assaults against the Atlantic routes. The German crews expected to systematically pick off vulnerable freighters. Instead, they slammed headfirst into an impenetrable wall of high-frequency direction finding, radar-equipped aircraft, and highly coordinated escorts. The brutal mathematics of the tonnage war violently flipped against the hunters. In just that single month of May 1943, the German Navy lost 43 U-boats. It was a catastrophic, completely unsustainable slaughter. A highly trained U-boat crew took years to cultivate, and the sophisticated submarines took many months to build. They were suddenly being annihilated faster than German industry could replace them. The American shipyards had not fired a single depth charge, but they had provided the unbreakable logistical spine that made the aggressive naval victory possible. By mathematically eliminating the threat of a collapsed supply line, the industrial miracle freed the Allied navies to break the back of the wolf packs. The entire German naval strategy was predicated on bleeding a fragile transatlantic artery dry. But by the summer of 1943, that artery had mutated into a heavily armed, unkillable conveyor belt of steel, and the German submarine fleet was being crushed against it. By the time the emergency shipbuilding program finally wound down, the sprawling network of American coastal yards had delivered a staggering final tally. Over 2,600 Liberty ships had been launched, fitted, and sent into the global supply chain. That number fundamentally broke the mathematical premise of the German tonnage war. When Admiral Donitz's U-boat commanders looked through their attack periscopes in the early days of the conflict, they saw a finite, fragile system. We must return to that initial, devastating image. A single torpedo striking a steel hull, the violent detonation, and a 10,000-ton cargo transport slipping beneath the freezing waves of the North Atlantic. For a German submarine crew, that image represented absolute victory. They had successfully destroyed the ship, eliminated its critical cargo, and permanently subtracted from the Allied ledger. But the strategic reality of the ocean had been completely inverted. What the submarine commander could not see through the crosshairs of his periscope was the vast, interconnected industrial machinery standing directly behind that sinking vessel. He was no longer just fighting the doomed ship in front of him. Behind that shattered hull were the sprawling, floodlit mudflats of California and Maryland. Behind it were the towering, heavy-lift cranes swinging 50-ton prefabricated steel blocks through the night sky. Behind it were the inland locomotive foundries, casting massive, triple-expansion steam engines, and the hundreds of thousands of newly trained welders working grueling graveyard shifts to fuse identical steel seams. The U-boat had destroyed an individual ship, but it was entirely powerless against the systemic pipeline of replacement tonnage. Before the torpedoed vessel even settled on the ocean floor, another identical hull was already sliding down a concrete slipway, ready to seamlessly take its place in the heavily armed convoy. The German strategy of attrition ultimately failed because it relied on an outdated understanding of maritime limits. They believed they were hunting a traditional merchant fleet that could be mathematically exhausted by localized tactical strikes. But you cannot win a war of attrition against an enemy that has completely decoupled itself from the constraints of traditional craftsmanship. The U-boats were aggressively targeting individual pieces of steel, completely failing to realize that the United States had not just built a bigger fleet. The emergency shipyards had industrialized the entire ocean. The entire German naval strategy was predicated on a lethal, intimate hunt, spending years in the lives of elite crews trying to bleed the transatlantic supply chain dry by destroying one isolated vessel at a time. It was a terrifyingly effective tactic, designed for a traditional war of maritime attrition that simply no longer existed. Ultimately, the brutal U-boat offensive failed not because of a sudden collapse in German tactical discipline, but because it ran headfirst into an entirely unprecedented and insurmountable industrial reality. Germany waged a relentless, mathematically calculated war against individual, vulnerable hulls of steel drifting across a freezing ocean. But they decisively lost that conflict because a submarine, no matter how stealthy or deadly, cannot torpedo a continental assembly line.